Dear students, in the last class we have studied about the symmetry elements. In the symmetry elements we have studied plane of symmetry, alternate axis of symmetry and center of symmetry with various examples. And also we have studied the laws of crystallography. In the today's class, you are going to study about the X-ray diffraction studies and the determination of crystal structure. As you know, in 1912, a German physicist, the Max van law, suggested that a crystal could serve as a three-dimensional diffraction grating provided the wavelength of incident radiations and the distances between the consecutive atomic layers in the crystals were of the same order of magnitude. X-ray with the wavelength approximately 0.1 nanometer or 1 angstrom fulfill this condition. Making use of this, the structure of crystal can be determined. William H. Bragg and his son William L. Bragg developed a simple equation for the study of crystal structure. According to them, a crystal could be employed not only as a transmission grating but also as a reflection grating. When X-rays are incident on a crystal face, these penetrates into the crystal and strike the atoms in successive planes. From each of these planes, the X-rays are reflected like the reflection of a beam of light. From a bundle of glass plates of equal thickness, based on this model, they derived a simple relation between the wavelength and the angle of incidence and the distance between the successive atomic planes. It is n lambda is equal to 2d sine theta. This equation is called Bragg's equation or Bragg's law. Let us study how this Bragg's law can be derived, that is, derivation of Bragg's equation. In this diagram, I have taken the two planes, plane 1 and plane 2, and I have taken the two incident, the X-ray. One is known as AB and its reflected form is BC, and the second which incidents on a second plane DE and the reflected is EF. First plane, there it makes an angle theta. Now, keeping this diagram, let us explain this diagram. Consider the two waves 1 and 2 incident on planes 1 and 2 respectively at an angle theta. The initial part of the two waves AB and DG are in phase. The wave 2 reflected from plane 2 travels a greater distance than wave 1 reflected from plane 1. Drawing BG perpendicular to DE, it can be seen that the path difference delta of the two waves, that is equal to GE plus EH. The part of the reflected wave BC and HF must also be in phase so that the two waves reinforce each other. This is possible when the path difference delta is either one whole wavelength or any integral multiple of it, that is n lambda. So we can write n lambda is equal to GE plus EH. From the figure, we can write angle GBE is equal to angle ABD, that's equal to theta, or we can also write this as 90 minus angle DBG. Similarly, angle HBE is equal to angle CBF, that's equal to theta. Since the two right angled triangles BGE and BHE are congruent, therefore GE is equal to EH. We can also write GE upon BE is nothing but GE upon BE is nothing but the distance between the two planes, where we can write this as small d, that's equal to sine theta. Therefore, GE is equal to d into sine theta. Now, since the path difference is nothing but it is 2GE, therefore it is equal to 2d sine theta. Since 2GE is nothing but it is a GE plus EH, that's equal to n lambda, therefore n lambda is equal to 2d sine theta. N is equal to 1 indicates the order of reflection is first order. N is equal to 2 indicates the order of reflection is second order, and so on. So this is how we can derive the Bragg's equation, which is the most important equation, known as n lambda is equal to 2d sine theta. Here also I have shown this Bragg's law, how the incident and the refracted ray from the two planes, it strikes and undergoes reflection, and d is a distance between the two planes, and the path difference is I have shown there. So this is another the slide showing the incident and reflection in case of the two planes of the crystals. I have also given a problem to you, so you solve this problem based on the Bragg's equation. Now, another point I would like to mention here, that is the determination of structure of sodium chloride by rotating crystal method. So in the rotating crystal methods, I have shown the three diagrams. So any one diagram you can have to write in the examinations. So the X-ray tube, where X-ray produces and it passes through the filters, and then it strikes on a crystal, and there it undergoes reflection, and in the detector we can see the reflected the ray. Based on this, the angle, we can find out the what you can say the nature of the crystal or the type of the crystal. In this rotating crystal method, a single crystal is mounted with an axis normal to monochromatic X-ray beam. A cylindrical film is placed around it and the crystal is rotated about the chosen axis. As the crystal rotates, sets of lattice planes will at some point make the correct Bragg angle for the monochromatic incident beam, and at that point a diffracted beam will be formed. Here also I have shown in the another slide with a similar information. Now let us discuss how this can be done. That is the determination of structure of sodium chloride by rotating crystal method. The apparatus used in the determination of the structure of sodium chloride crystal by rotating crystal method is shown in the figure. I have shown the three figures, any figure which you can refer. The X-rays generated in the tube is made monochromatic by passing through a filter C and then through the slits D and E to get a sharp and narrow beam. The X-ray beam of known wavelength is allowed to strike sodium chloride crystal mounted on the turntable, which rotates with uniform angular rate. The rotation causes sets of planes coming successively into their reflecting positions. The intensities of the reflected rays are measured on a recording device R and glancing angle theta for each intense reflection is recorded. By applying the Bragg's law, ratio of the lattice spacing for various groups of planes can be obtained. By comparing experimental and calculated ratio, the structure of sodium chloride crystal is determined. The structure is phase-centered cubic lattice. For phase-centered cubic lattice, the ratio of the distance d between successive planes is 1 is to 0.747 is to 1.154 for first order reflection from the D100 is to D110 is to D111 phases. In the case of sodium chloride, the experimental values of theta for first order reflection from D110 is to D110 is to D111 phases are 5.9 degree, 8.4 degree and 5.2 degree respectively. Now, by putting these theta values in the Bragg's equation, I get lambda upon 2 sine 5.9 degree is to lambda upon 2 sine 8.4 degree is to lambda upon 2 sine 5.2 degree. So this ratio also comes to be 1 is to 0.705 is to 1.14. Since theoretical values matches with experimental values, hence sodium chloride has phase-centered cubic lattice. This is how the crystal structure is determined based on X-ray diffraction studies. Students, go through the X-ray diffraction studies and the determination of crystal structure. Thank you.